Imagine you're handed a mission. You need to build a global word lookup service for millions of users. It has to hold every single word and every meaning. Sounds pretty simple, right? But then comes this impossible constraint that completely breaks every instinct you have as a back-end engineer. You cannot use a database. No PostgreSQL, no MongoDB, no Redis. Literally nothing. Just flat files, object storage, and your stateless application servers. Welcome to the Explainer.
Now, this isn't just some cruel theoretical puzzle. We are talking about massive scale here. 170,000 words, totaling one entire terabyte of data. And it requires exact key lookups and weekly updates. It demands we completely rethink how we interact with data from the ground up. Okay, let's dive right into our blueprint. 1. The constraint. 2. Storage compute separation. 3. The perfect file. 4. Atomic updates. 5. Production hardening. And 6. The big picture. Let's get to it.
Part 1. The constraint. A dictionary without a database. Let's unpack this constraint and talk about why we are actively fighting that just use a database reflex we all have. Whenever we hear the word lookup, our brains immediately scream for a database. But think about our actual access pattern here. We've got 170,000 words, the data is read mostly, it's totally immutable between those weekly updates, and it relies strictly on exact key access. Bringing in a traditional database with all its replication, failover, schema migrations, and connection pooling, that's essentially using a sledgehammer to crack a walnut. We just don't need all that operational tax.
Part 2. Storage compute separation. The paradigm shift. To actually build this effectively, we have to embrace a fundamental shift in how we think about architecture: storage compute separation. In a classical database, the storage disk and the query engine are physically and logically fused together. You can't scale one without the other. Think of that coupled architecture like a kitchen, where every single chef has their own private pantry locally. If you hire a new chef, you gotta stock a whole new pantry. If a chef leaves, you lose that pantry's food. But with a separated kitchen, which is our cloud-native approach, the pantry is just a giant shared warehouse, and the chefs are totally interchangeable. By using stateless API servers that simply fetch from an infinite, durable S3 storage layer, we achieve massive elasticity. You could literally lose every single compute server, and your data is still perfectly safe.
Part 3. The perfect file. Designing the layout. So our compute layer is stateless. Great. But how on earth do we actually store 1 terabyte of dictionary data on S3 so our servers can query it instantly?
Well, the naive approach would be to just dump 170,000 individual text files into an S3 bucket, one for each word. Don't do this. That is an absolute operational nightmare. It destroys portability, it racks up massive S3 request costs, and it makes atomic updates practically impossible. Instead, the right layout is one single, massive file divided into 2 logical regions, a sorted index section and a data section. We completely separate the metadata from the payload.
But of course, that brings up a really critical question. How do we design that index so it maps words to their exact byte locations without completely exhausting our server memory?
There is a huge trap here that many engineers fall into, and it's the 32-bit limit. A common instinct is to use standard 32-bit integers to record those byte offsets in the index. But listen, a 32-bit integer maxes out at 4 gigabytes. Our file is a full terabyte. If you use 32-bit offsets, your system is going to silently corrupt your data. You absolutely must use 64-bit offsets for the index. And the crazy part? Even with the right 64-bit data types, our entire index of all those words takes up a tiny 3 megabytes of RAM. That tiny memory footprint enables an absolute superpower: byte-range fetches. Because the server holds that 3 megabyte index right in RAM, it knows exactly where every single word lives inside that 1 terabyte file. It doesn't download the whole file. It just tells S3 to fetch only the specific 50 or 80 bytes needed for that exact definition. Let's look at how this builds the read path. When a user asks for a word, the API server probes its in-memory hash map. It instantly finds the exact offset and length, issues a single byte-range GET request to S3, and returns the meaning. That is 1 memory read and 1 network round trip. We've completely inverted how a traditional database query planner works. Part 4. Atomic updates. Mutating the immutable. Okay, serving reads is solved, but what about writes? We have weekly updates. How do you mutate a 1 terabyte file without causing downtime for the users? The simple answer is, we don't. Mutation is the enemy of operational sanity. Instead, we use a changelog merge. We take the old dictionary file, we take the new changelog, and we run a linear time merge of those two sorted lists to build an entirely new file on a temporary build server. Every single update produces a pristine, brand new file, and that makes rolling back as trivial as just pointing back to the old one.
However, rolling out a new file introduces what we call the atomicity problem. What happens if an API server is still holding the old in-memory index, but you swap out the S3 data file? Say the old index points to byte 100 for the word apple, but in the new file, byte 100 lands right in the middle of the word aardvark. The user gets total garbage data.
To fix this, we implement the pointer file pattern. We upload every new dictionary file to a totally unique path on S3. Then we use a tiny meta.json file that literally just points to the currently active version. Because overwriting that tiny JSON file in S3 is a fully atomic operation, it acts as a flawless instant switch. So your API servers need to pick up this new pointer. You actually have a few options here. You could use reactive pub sub for lower latency or tie it to your rolling deployments. But honestly, the best staff-level default is just simple periodic polling. Every few seconds, the server checks that meta.json file. When it sees a new version, it gracefully downloads the new 3 megabyte index, swaps it in memory, and seamlessly transitions to the new data file without dropping a single user request.
Part 5. Production hardening, surviving reality. We have a working architecture now, but surviving reality means we need production hardening. A principal engineer knows we need absolute format portability and deep safety checks.
A crucial point here is how the API server reads the file. A junior engineer might just use a string separator, like inserting end of index, to split the file sections. But what if that exact string naturally appears in a word's definition? It completely breaks the parser. Instead, we use fixed width headers. Just like a PNG or a Parquet file, the first 64 bytes of our file declare exactly where the index and data live. This guarantees O of 1 parsability every single time.
And this creates a beautifully efficient boot flow. Picture this. A brand new server spins up. It does a tiny byte range fetch for just that 64-byte header. It learns exactly where the index is. It does a second fetch for the 3 megabyte index, and boom, it is serving traffic. The whole boot process takes under a second, and it completely ignores the 1 terabyte payload until a user actually queries it.
Now, to make this truly bulletproof, you have to ask the hard questions. How will it fail? How will we know? And how do we roll back? You've got to add CRC32 checksums to prevent corrupted reads. You use E-tag conditional write so concurrent builds don't accidentally clobber each other. You need to track red metrics, rate, errors, and duration. And you definitely maintain fallback caching of that meta pointer. That way, if S3 has a hiccup, your servers just keep humming along on the last known good version.
Part 6. The big picture. Data lakes. By now, you might be sitting there thinking, okay, this is an incredibly clever trick for a dictionary. But let's zoom out for a second. This pattern we just explored, it's fractal. This hyper-focused 1 terabyte file architecture is the exact same blueprint used by massive petabyte-scale data lakes. Systems like Apache Iceberg, Delta Lake, Snowflake, Athena, they all use immutable files, pointer manifests, separate metadata headers, and byte range fetches against object storage. By figuring out how to build this dictionary, you have fundamentally learned how the modern cloud data stack actually works. Which leaves us with this final thought. Next time you are facing a system design problem, before you reflexively reach for a massive, expensive database, just pause. Look at your access patterns. Look at your failure modes. Because if you can build a terabyte-scale, infinitely elastic lookup service with nothing but a flat file and a few clever byte range fetches, what else in your architecture can you decouple? Seriously, go try building this exact system yourself locally this weekend. I guarantee it will completely change how you look at system design.